Alright, we're back again with line integrals. We're going to look at scalar line integrals and figure out kind of what makes them scalar. Alright, so I want you to imagine that you have a function that is in terms of x and y that gives an output, and that output will be called f of x and y. Just for an example, perhaps in this 2D plane, the xy plane, perhaps there is an associated temperature value with every point in that 2D space. So really, what this f of xy is describing is only valid within this xy plane. So here's the x, here's the y. So don't try to think about the f of xy as a third dimension. It's not. It's actually a scalar dimension, which is going to tell us what the output of any given order pair is. So for example, what if I wanted to know what the temperature at this point in the xy plane was? Well, I would look at its x and y inputs, and that would give me an output, f of xy, which in this example would be temperature. Maybe it's 20 degrees C here and 30 degrees C there. The whole point of a scalar function is that for every ordered pair there's going to be an output, and that output's going to give you a scalar value for that point in 2D space. You can also have a function of x, y, and z, and now you're looking at a scalar field in 3D space, but now that scalar field is a fourth dimension. I try to keep it to a third dimension, just because I can't draw in 4 dimensions. So one thing to quickly notice is I might even do a video about this. There's a lot of different signs in vector calculus, and there's not a whole lot of explanation as to what the difference between them is. As far as I can tell, dr, which is a vector, the absolute value of the vector dr is ds. And so remember, r is our vector curve function, and it's parameterized. And if we take the absolute value of that vector, we'll get the length of that dr. So we'll need this in just a minute. So here's our scalar surface. This is going to tell us what the temperature is. Looks like we have a maximum temperature at the origin. And as we go off in either direction in this quadrant, the temperature drops. Alright, so what we're trying to do with a scalar line integral is if we take a path, so our path is going to be this parameterized curve r of t, which is going to be a vector function. It's going to give you this curve on the bottom here. And so this tells you the path that you're taking in 2D space. Now what we want to find is we want to find the area between that path and the scalar valued function. So in other words, we're adding up all of the temperatures for each given point from here all the way to point B. So from A to B, we're adding up all of the temperatures times the segment lengths. And so if we zoom in on one of these thin rectangles, just like we integrated with Riemann integrals, now we're doing this with a line integral. So we take this curve, this curved surface, and we look at it. So we've cut this up into many rectangles, and we look at that rectangle, and you'll notice that the width of that rectangle is ds. So in other words, the magnitude of our vector r, we're going to call it ds, and that's going to be a small chunk of the segment of this curve. And you'll notice that ds has a dx and a dy component. Although these are technically scalar, they're no longer vectors, but there's definitely a dx component and a dy component of ds. I suppose I should call this dr if we're going to be doing components. We'll call it dr. And so the height of this rectangle is f of xy for whatever ordered pair you're at. So in other words, if I wanted to know what happens at this point, I would plug in x and y to my f, and I would get my f of xy as this height. And so when we look at this from the side, we'll notice that the area of this thin rectangle is the length of the segment times the height of the scalar function f of xy. And so what we're looking for is we're looking to add all of these rectangles together, infinitely many of them, which kind of points us towards integration. And so the idea is we're going to integrate this area for all areas. And so to do that, we're going to find that the area of just a small rectangle, which is fxy times ds, gives us the area of this rectangle. And then we're going to integrate all such rectangles that exist on this path from point A to point B. And that will give us the area under the curve from point A to point B. And as usual with vector calculus, there's a few tricks that help us calculate this in terms of time. So to take a look at it, we can see that dr, the vector component of this line segment, is a vector function that is in terms of dx and dy. And so if we take the absolute value of dr, we end up with ds, which stands for the infinitesimal segment length. And that's going to be equal to, using Pythagorean, because look, all this is right here, there's dx, dy, it's a right triangle, and so dr is going to be dx squared plus dy squared all under the root. And so ds equals the square root of dx squared plus dy squared all under the root, just Pythagorean identity. And now what we want to do is invent a time so that we can integrate this with respect to time, because if you'll remember, our curve r is parameterized with time. So we need things to be in time to integrate them in this method. What we can do is we can actually pull out an imaginary dt squared out of dx squared and dy squared. Just to kind of show you that this is true, let's take a look at just one of these. So if I had dx squared, let's write it like this, dx squared, and I wanted to pull out a dt squared, I could pull out a dt squared, and then I would just end up with a dx over dt squared. And you can prove this to yourself, because if I multiply this inwards, the dt squared cancels with the dt squared, and you're left with dx squared. So all we're doing here is we're introducing a dt. And that's what I've done here, is I've pulled out a dt squared out of the dx and the dy squared. And because of that, now it's dx over dt squared and dy over dt squared, all factored with dt squared. But what we're going to do is we're going to take just the radical for dt squared. That's going to pull it outside of our radical, and we're going to end up with ds equaling the square root of dx dt squared plus dy dt squared, all multiplied by dt. And you may recognize this as a way to calculate arc length for parametric curves in even 2 dimensions. And so this is something you've seen before in Calc 2. Now, once we know this, we can actually plug it into our definition of a scalar line integral. So if we know the function f of xy, and we know the segment length of our parameterized r of t, then we can plug these two in together and solve at that point. And so that is how we deal with a scalar line integral. Next video we'll be talking about the vector line integral. Have a nice day.